Hello everyone, welcome back to Math with Allison. Today we're continuing our series on integration, so we're going to be talking about inverse trig. So let's go ahead and dive into it. We already know some of the inverse trigonometry. So we have inverse sine of x, inverse tangent, and inverse secant. These are going to be the most important in integration. But what happens when we add in some scalars there? So let's go ahead and talk about this problem right here. Our first step is always to bring out that scalar multiple. So I'm going to bring out that 4. And now we have inside the radical 9 minus x squared. So notice this is very similar to the inverse sine of x. But in inverse sine of x, we have this is equal to 1. In our case, this is equal to 9. So our issue is that we need that to become a 1. So let's go ahead and talk about how we can make that happen. First, I'm just going to rewrite it. I know that it's a square, so this becomes 3 squared minus x squared dx. Is I'm going to go ahead and multiply the denominator by the square root of 1 over 3 squared. But whatever I do to the denominator, I also have to do to the numerator. And so I also have to multiply this by 1 over 3 squared. And of course, that dx is still here. So we will see the purpose of doing this. So I know in the numerator, this just becomes 1/3 because of the square root. So I can go ahead and bring that out front, and I get 4/3 out front. Now in the numerator, I still have a 1 because I pulled out that scalar, but let's talk about what happens to the denominator because that's the interesting part. So in the denominator, I get the first term becomes a 1 because I divided it by itself. But now we have minus x squared divided by 3 squared dx. So like we talked about over here with inverse sine, we also have that this right here is a whole quantity squared. So I want to change that in our problem. And I'm going to go ahead and rewrite this instead of each one individually squared. I'll just write it as x divided by 3 quantity squared. So now our next step is to set that value equal to u. Once that we have this right here is a value of 1, we can set whatever is left over in here inside the square root equal to u. So let's go ahead and do that. So u is equal to x divided by 3. We're going to go ahead and take the derivative in terms of x of both sides, so I get 1/3. And remember, we want to go ahead and get dx all by itself. So I'm going to cross multiply, and I get 3 du is equal to dx. So let's go ahead and replace these in our equation. So we have 4/3, that did not change at all. And we get 1 over the square root of 1 minus u squared, and then times 3 du. So notice here, actually, our 3 cancels out. So now we're just taking the antiderivative. Now that is something we can integrate. That becomes 4 times inverse sine at u plus c. But of course, we want to go ahead and replace u back in. So this becomes 4 inverse sine at our u value, which is x divided by 3 plus c. So the trick of how this works is we get 1 over a squared minus x squared dx is equal to the inverse sine of x divided by a plus c. So notice in our equation, we had a value of 9, which was equal to 3 squared. And so it ended up being x divided by 3 in our final solution. So that trick is going to work every single time. So now let's go ahead and think about arctangent. So in this one, we have a value of 16 instead of a value of 1. So our first step is to go ahead and rewrite this. I'm going to bring out that scalar of -1. So now I have a 1 in the numerator, which is what I like to see. And I'm going to rewrite this as 4 squared plus x squared because this tells me what I'm going to go ahead and multiply by. I'm going to multiply the denominator by 1 over 4 squared, but whatever I do to the denominator, I also have to do to the numerator. So if I rewrite that, I get -1, and I'll bring out that 1 over 4 squared, so that becomes over 16, and then that 1 stays the same in the numerator, but now I get 1 plus, and that becomes x divided by 4 quantity squared. So this tells us what we're going to go ahead and set that u equal to, because we have our 1 right here, and we have a 1 right here, so we're pretty happy. We're going to go ahead and set u equal to x divided by 4. So du dx, when I take the derivative of both sides, is equal to 1/4, and we can go ahead and cross multiply. So I get 4 du is equal to dx. So let's go ahead and fill in all those parts here. I get -1 over 16 times the integral. That 1 stays the same, and we get 1 plus u squared times 4 du. So notice what cancels here. that 4 cancels with one of the 4's in the 16, so that remains a 4 in the denominator. So this becomes negative 1/4. And now we have something we can take the antiderivative of. We're happy because this is a 1, this is a 1, and then this is a quantity u squared. So when we take the antiderivative, that negative 1/4 hangs out, and we get arctangent or inverse tangent of u plus c. But of course, we want to go ahead and replace that u back in. So we had u is equal to x divided by 4. So again, this shows us our trick, which is when we have 1 over a squared plus x squared, where a is any number, we have to multiply it by 1 over a tangent, inverse tangent of x divided by a plus c. So notice in our final solution, we got that 4 down here, and we have x divided by 4 right here. So we have one more trick we're going to go over, and this has to do with inverse secant. So here we have 3 divided by x times the square root of x squared minus 4. So, of course, what we're going to do first is we're going to bring out that 3. And I rewrote the 4 as 2 squared because we want to make that a 1. And now we know what we have to multiply by in order to make that 1. So I need to multiply by the square root of 1 over 2 squared. And I'm going to also multiply that to the numerator. So remember, this whole thing right here is just equal to 1/2. So we can go ahead and bring that 1/2 out front. So this becomes 3/2. That x stays the same on the outside, but now we have something new on the inside. We can rewrite that as x over 2 quantity squared minus 1. So now that we have that this value is a 1 and this value is a 1, we're happy to go ahead and use u substitution in order to make this right here more along the lines of what we want to take the antiderivative. So we're going to go ahead and set u equal to x divided by 2, and we're going to differentiate. So let's go ahead and fill in what we know. So that 3/2 stays the same. That x stays the same in the denominator. We haven't done anything to it yet. And that becomes u squared minus 1 times 2 du. Notice that the 2's cancel out. But we also have to pay careful attention to this x in the denominator. I can't integrate yet because I want everything to be in terms of u. So actually what we're going to go ahead and use is what u is originally equal to. So if I bring this down and I multiply both sides by 2, I get 2u is equal to x. And I can go ahead and replace that in our equation. So instead of x, I get 2u times the square root of u squared minus 1 times du. But again, we're not quite finished because I want to bring out the scalar multiple. So I'm just going to bring it out as 1/2. Alrighty, now this is something we can take the antiderivative of. So that 3/2 is just a scalar multiple, so it hangs out. And this becomes secant or arcsecant of u plus some value c. And of course, we need to replace u back in. So notice here when it was 2 squared, what we ended up with is 3 divided by 2, inverse secant of x divided by 2. So that weighs into our trick where we have the integral of 1 over x times x squared minus a squared is equal to 1 over a inverse secant of x divided by a plus some value c. So overall, the inverse trigonometry involved in integration is going to be these 3 integrals. So this has to do with inverse sine, inverse tangent, and inverse secant. So if you don't enjoy memorizing or it's difficult for you, you can always whip out u substitution. So if the process makes more sense, that totally works. If you like the formulas and you like to memorize the tricks, that also works. So it's whatever your heart desires. But that's all I have for this video today. If you enjoyed it, I have many more videos like it, so make sure to check out my playlist. They're linked down below. Otherwise, please give this video a thumbs up and comment other problems or topics you'd like to see done. Thanks for watching.